Okay, so 74, we're trying to find the area of this trapezoid. I've drawn it a little bigger. Just this diagram is a little small. It seems like whenever I try and zoom, my OneNote stops working. So this one's going to involve a fair amount of steps here to find. So we have one side up here, 18, and we have this piece down here, 24. These are the PQ and SR are the parallel sides. Well, we need this base down here, and we need this height in order to actually find the area. So the fact that we see 30 degrees here maybe should give us a clue that we're going to be working with 30, 60, 90 triangles. And also, if you remember in a trapezoid, well, because we have two parallel lines cut by a transversal, this angle here is going to be 45 degrees. This 45, these need to be supplements, and then also these need to be supplements too, this full angle. So I'm going to go ahead and draw this height in as well. And so that's going to be a 45, 45, 90 triangle on the left and a 30, 60, 90 triangle on the right. So I'm going to draw all these in so you can see all the pieces. And that's going to be the key to unlocking this problem here. So this triangle over here, the 45, 45, 90, we don't have anything to really work with. So I'm going to check out the 30, 60, 90 triangle. Well, we do have the hypotenuse of that triangle. And so we know that the side across from 30 is always half the hypotenuse. So now we've got the height of this trapezoid, which is 12. And then we can, this leg, this part of the trapezoid here, that side is going to be 12 times the square root of 3, because that's how we get the side across from 60, is to take that smaller side and multiply by square root of 3. We know that the height is 12, so I'm going to go ahead and write that height over here. Because this is a 45, 45, 90 triangle, it's not really drawn to scale here, but we know that this part right here is also going to be 12, because it's isosceles. And we could write that this side's 12 root 2. I don't think we're actually going to need it, but just for completeness, I'll go ahead and write it there. Because this leg is 12, we know that this part here is 6. I'll just erase that a little bit here, because we know the whole thing is 18. And so, because this is a rectangle, then we can carry down this 6 to this part right here. And so we have base 1 here, up at the top, equals 18. Base 2 is this entire section right here. We have to add two pieces, a 6 plus a 12 root 3. And then we have the height here, which is 12. And then for the area of a trapezoid, we do the average of the bases. So 1/2 base 1 plus base 2 times the height. 1/2 of 12 is 6, so I'm going to go ahead and simplify that. 18 plus 6 is 24, plus 12 root 3. And then we distribute that 6 to get 144 plus 72 root 3. And that's the answer in units cubed. Some of you may have gone to decimals or something here, but because these are 30, 60, 90, and 45, 90 triangles, I think it's easier to keep it in terms of radicals. But if you got the decimal equivalent of that too, it would not be wrong. Height of the trapezoid, if the area is 210, so we're looking for this side right here, or this height, which is the same as that side. If you want to just go with the formula approach here, we know the area of a trapezoid is the average of the bases times the height. 1/2, we have the two bases here, 18 plus 24. Halfway in between there is 21, so this will simplify to 21. We don't know the height, and we know that the area is 210. So 210 equals 1/2 of, well, 18 plus 24 is 42. 1/2 of that is 21 H, and then so H will be 210 divided by 21, which is just going to be 10. Oops, 10. I'll just show you another way to think about it without the area formula. If I drop this height down here, I know that, well, actually I'm just going to skip that one for now. Let's go with the formula approach here. Another trapezoid problem, this time with no diagram, so we have to draw our own. So we have an isosceles trapezoid. So that means that the legs are congruent. And see, the bases are 20 and 28. The legs are 5. We need to find the area. So we have base 1 and base 2. We don't have the height. So we're going to have to back into that a little bit here by drawing this down. So we know that this segment here is going to be 20, which gives it, so 28 minus 20 is 8 in total. So between these two sides here, or two triangles here, we have to divide it in half, because it's isosceles, we can do that. That side is going to be 4, this piece is going to be 4, so 4 plus 20 plus 4 gets us back to 28, so we did that right. And then, you know, you could do Pythagorean theorem here, but this one's a triple, almost everyone remembers, a 3, 4, 5 triangle. So we have a 5 in the hypotenuse, 4 here, the height has to be 3, and that gives us all the information we need, because the area is 1/2 base 1 plus base 2 times the height, and base 1 is 20, base 2 is 28, halfway in between is 24, so I know that that's going to end up being 24, because that's the average. So 1/2 of 20 plus 28 is 24, times 3 would give us 72 units squared, which is E. 77, so now we're moving on to a problem with squares. The perimeter of a square is 100 inches. Find the area of the square. Well, this one hopefully is pretty straightforward. If all the sides of the square are the same, so the perimeter is going to be 4s, that equals 100. So s equals 100 divided by 4, or 25. So we know a side of this square is 25, and we know that the area of squares is base times height, which is just going to be 25 times 25, or 625 square inches. So a lot of time in area problems, we either need to add two pieces together to get an area, or take one big area and subtract another area. So this is going to be, I'll call it a big minus little type problem. So the big rectangle, we can find the area of that, so we're going to find the area of everything. This is going to be area big is base times height. These are just rectangles. Even though it's not shown, we're going to assume that they're rectangles. Base times height is going to be 12 times 7. And then the area of the piece that we want to take out is this guy right here, which is 8 by 2. So the area of little is base times height, which is 8 times 2. That's going to be 16. 12 times 7 up here is 84. And now we're going to subtract these two numbers to get the area of the shaded region. So 84 or 68 looks like the difference here. And we're in inches, so we have inches squared. So we're going to find the area of the rhombus here. Well, see, there's different ways we could approach this. One is it's a parallelogram, so we could do area equals base times height if we could find those pieces. We definitely have a base here of 10, but as we're looking through here, there doesn't seem to be an obvious way to get the height. So we'll just put that idea in the parking lot for now. Another one is rhombuses are always 4 congruent right triangles, so we could see if we could find the area of one of those triangles. And looks like that could be a promising strategy here. So these are right angles, even though they're not drawn as right angles, they're drawn in there. We know it's a right angle, so we have to think about, in order to find the area of that triangle though, we need a height. So we need to have this area I'm drawing right here. So if I just redraw that triangle, looks like 10 is the hypotenuse, 8 is one leg, and the other leg is, you can recognize this as a multiple of a 3, 4, 5. So 6 would be the other side, by recognizing the Pythagorean triple. Or you could always just do, b squared equals hypotenuse squared minus 8 squared to get 36. Square root of 36 would be the side, which would give you 6. Once we have that, we could find the area of one of those triangles, 1/2 base times height, and that would be 1/2 times 8 times 6. So 8 times 6 is 48, divided by 2 is 24. But we have 4 rectangles, so we have to multiply that answer by 4 to get 96 square units. So approach 1 didn't work. Approach 2 was add up the triangles. Approach 3 would be, if you feel like you have to memorize formulas, the area of a rhombus is always 1/2 diagonal 1 times diagonal 2. I don't like to memorize that because it doesn't really, it's hard to see exactly why it works. So I always like to do the triangle approach I just showed you, but we could do that. We could try this here. Diagonal 1 we know is 8 plus 8, so we have that as 16. The other one, we still would need to do this little triangle idea to figure out the other diagonal, so this would be 6 and 6. So 6 plus 6 is 12, so that diagonal is 12. So the area would be 1/2 16 times 12. And 16 divided by 2 is 8. 8 times 2, 12. 8 times 12 is also 96. Another rhombus problem here. We have the diagonals of a rhombus are given as 32 and 10. We know that the rhombus diagonals are perpendicular and they bisect each other, so if we wanted to, we could divide this up into 16 and 16, 5 and 5, and you could use that same approach of the area of one of these triangles is area is 1/2 base times height, which would be 1/2 16 times 5. 16 divided by 2 is 8, that's 40, but we have 4 of those triangles, so the area would be 160 units squared. Or you could go with the area is 1/2 diagonal 1, diagonal 2, which is kind of what they're baiting you to do here with just giving you that information. But 1/2 32 times 10. 32 times 10 is 320. 320 divided by 2 is also 160 units squared.